So let's talk about something being strong or weak as an acid. Actually, this falls more into the category of understanding dissociation reactions. In dissociation reactions, you have a species, AB, which is typically going to be a cation and an anion. And it's going to go into solution, and it's going to make a positively charged species and a negatively charged species. We actually talked about this when we were doing solubility reactions just a lecture ago. And if you recall, at that point, we were able to discern between what we called soluble salts, like NaCl, which had KSPs that were approximately infinite. We knew that they weren't. They were actually more like 5 or 10, but they were approximately infinite. And what we called sparingly soluble salts. Salts like calcium carbonate, for example, that had KSPs that were, I don't know, on the order of 10 to the minus 10 or 10 to the minus 30. Very small numbers like this. Well, what's nice is that there's this amazing parallel, very simple, obvious parallel between soluble and sparingly soluble salts and strong acids and bases and weak acids and bases. Very simply, the parallel is this. The soluble salts, like sodium chloride, are the equivalent of the strong acids and bases. Why? Because a strong acid or base, when thrown into water, is going to go from 100% of the HA to, at equilibrium, none of the HA and 100% of the proton and its conjugate base. If that's the case, then just like with soluble salts like sodium chloride, that you would argue that the K was approximately infinity. And sure enough, although it is not actually infinity, and in fact is nowhere near it, the fact that that complete dissociation has occurred is how we define something being strong. Equivalently, we say that something is a weak acid or base because when we throw it into water, not very much of it dissolves. We may start off with 100% of it, like this, and then when we're done, only about 1% of it actually dissociates. Basically, nothing happened when we threw it into water. The K under those circumstances is very small. Maybe it's 10 to the minus 10, something like this. Notice the analogy here to our sparingly soluble salts. Strong electrolytes are the soluble salts and the strong acids because they dissociate completely to make, according to this, a K equal to infinity with the approximation that every bit of it became dissociated. Sparingly soluble, weak, refers to the fact that only a tiny fraction goes into solution and forms the ions. The classic picture that you always see to prove or support this is the idea of having a beaker with some water in it, and you've got some electrodes that go into it, and you're trying to light a light bulb. If you throw a soluble salt or you throw a strong acid into water, it makes lots of ions, it lights it up. If you throw a sparingly soluble salt or a weak acid into solution, it doesn't light the light bulb, or it lights it only very dimly. So as we look at today's lecture, we're going to be looking at the strong acids, and in our next lecture, we will be looking at the weak acids. And the distinction is the amount of them that dissociated in water.